Hello.
Good morning, sir.
Good morning. Can you hear me? Hello.
Yes, sir.
Yeah. Okay. Okay. So we'll just wait for others. Okay.
Yeah, so within a minute we can start.
Sure. Sure. Okay.
Anila, ma'am?
Yes, ma'am. Shall we start?
Yes, ma'am.
So, very good morning to all faculty members, our eminent speaker, Dr. Vimal Bhatia, and dear participants. I welcome you all on day 2, session 1 of AICTE ISTE 1 week online refresher program on artificial intelligence in Cooperative Noma 5G network. I would like to welcome our eminent speaker, Dr. Vimal Bhatia, Professor IIT Indore. It's my pleasure to introduce him. Dr. Vimal Bhatia is currently working as a professor with the Indian Institute of Technology in Indore and is an adjunct faculty at IIT Delhi and IIIT Delhi. He received PhD degree from Institute for Digital Communication with the University of Edinburgh, UK in 2005. During PhD, he also received the IEEE Fellowship for Collaborative Research at the Department of System and Computer Engineering, Carleton University, Canada, and is Young Faculty Research Fellow from MEITY Government of India. He is also a recipient of Professor SVC AIA Memorial Award in 2019. He has worked with various IT companies for over 11 years, both in India and UK. He is a PI, co-PI, coordinator for external projects with funding of over USD 17 million from MEITY, DST, UKIEI, RI, MOE, AKA, IUSSTF, and KPMG. He has more than 300 peer-reviewed publications and has filed 13 patents. He has supervised 15 defended submitted PhD theses. His research interests are in the broader areas of communication, non-Gaussian, non-parametric, signal processing, machine deep learning with application to communication and photonics. He is a reviewer for IEEE, Elsewhere, Ville, Springer, and IET. He is currently senior member of IEEE Fellow, IET Certified SCRUM Master. He was also the General Co-Chair of IEEE ANTS 2018 and General Vice Chair for IEEE ANTS 2017. He has served as a founder head of Center for Innovation and Entrepreneurship, Associate Dean R&D, Academic Affairs. He has delivered many talks, tutorials, and conducted faculty development programs for the World Bank's NPIU, TCube Third, and invited talk at WWRF 46 Paris. He is currently associate editor for IET Technical Review, Frontiers in Communication and Networks, Frontiers in Signal Processing, and IEEE Wireless Communication Letters. I welcome you, sir. Now I would like to invite Dr. Vimal Bhatia to deliver his talk on Introduction to NOMA in Beyond 5G Networks.
Hello. Good morning. Thank you very much for a detailed introduction. Yeah, I'm actually more. I usually use Google Meet. So this platform, I'll try to use the best I can. So yeah, thank you very much again for hosting me in this. And I saw the this program is mostly focused on NOMA and various aspects of NOMA in the future communication systems that we are expecting, maybe beyond 5G era. So today I've about an hour and a half. So roughly, I'll first start with small introduction on about our group, what we are trying to do, and then we'll delve deeper into power domain NOMA. And if let's say time permits, we'll go over a couple of other similar things. Like we are working on full duplexing and energy harvesting and all, how they can also be introduced in NOMA. So they are all, I'll say allied technologies. They are not, competing with each other. They are going to supplement each other. So they will be, working together, for the future communication systems. So let me first share my. Hello, I think somebody accidentally unmuted. Yeah. Okay, so let me share my slides. Okay, so this is. Okay, I can. So I can attach this. Yeah, attach. So share content. No, it used to be okay.
The upward arrow is there.
Yeah. So when I click on it, it says presenter mode, content
Yeah.
only. Okay, content only. So if I click on content only, then window nine windows. Okay. Yes. So no, yeah. Okay. It wasn't too difficult. Okay. Thank you. So I guess now it is visible. The slides are visible.
Yes, sir, it's visible.
Okay, perfect. I'll make it full screen.
Yes.
Oh, what happened here? No, it's changed slide to the other one. Change slide to full duplexing. No, no, it was. Yeah, okay. Yeah, so now you can see the slide. It says Signals and Software Group at IIT Indore.
बस हो जाएगा 4 तो करना है
एक सेमेस्टर में 4 होती है.
So is that the one that you see? Hello.
Yes,
Yes,
sir.
sir.
It's visible, sir. Slides are visible.
Visible, na? Yeah.
Yes,
Okay,
sir.
so you see the group highlights one, yeah? This is the slide that you're looking
Yes,
at
yes,
now.
sir.
Slide
Yes.
number 2, group highlights. Okay, perfect. Thank you very much. Yeah. So let us start. So we're doing a lot of work on the performance analysis of beyond 5G networks. So that's where we started with cooperative networks, and then now we have been working on NOMA for about 6 years now. We had
Hello, sir.
Pratik
Good morning. Hello, sir.
Hello, good morning. Yeah, good morning.
Hello, good morning. Sorry to interrupt you, sir. Sir, your volume is too low. We can't hear.
Oh, volume is low. Okay. Let me.
Screen is visible, but volume is too low, sir.
Okay.
No, ma'am, volume is not low. Actually, it is perfectly audible.
Okay, I was 74%. Now I'm 100% now.
Yes, ma'am. Volume is perfectly audible. Sir, voice is. Kindly check your network, ma'am.
Okay.
Yeah. Okay. Yes. So work has been on, beyond 5G networks where we have been working on NOMA, and I think we had one of the first full thesis on power domain NOMA in the country, which got submitted last year back, couple of years back. So here we'll go over this in detail in the later slides. And the next work that we are also deeply into is on adaptive signal processing, machine learning, deep learning algorithms for 6G and some of the other biological applications. So with that I mean things like looking at uh, if the seed is viable to be sowed, if there's a disease that is coming to a plant which is going to be bad in a few years. So those kind of applications. So mostly on the plants, we have tried this with collaboration with our local partners at IIT and along with Soybean Research Center here in Indore. The other technologies, OFDM, MIMO, NOMA, this is something you would have heard about in this FTP and others as well. Then we are working actually heavily on the visible light communication systems as well for 5G and 6G applications. So it has not made the standard so far in the 5G standard, but hopefully in the future it will come in. Or there's another parallel one which is IEEE line of standards. So we are expecting it to be coming there. Then some other work we do on optical and quantum networks. This is something we started with looking at elastic optical networks because you see our current infrastructure, all ICT, these talks and we are connected all over the world. It's all carried by optical fiber networks. So I mean, access network is okay. We can have optical or Wi-Fi or other types, but then going back on the backbone, it is our optical networks. Now, moving forward with the so I'm looking from the security point of view, and as we know that in this decade, quantum is going to be the next big thing. So we are also working on quantum communication networks, or again optical networks, looking at QKD, quantum key distribution, how it can be transferred, and that is not like limited to only on the optical networks. It is for satellite, also for I'm seeing recently some papers on wireless as well, MIMO wireless as well, looking at quantum key distribution. So this again one of the good areas that are coming up. Then of course we did one is on radar signal processing, looking at interference and things how we can detect small board in the presence of clutter and other artifacts, and been working closely with the industry and defense. So we have active collaborations across the world from UK, Ireland, Norway, Finland, Czech Republic, now South Africa, US, and we are executing projects from various agencies, international and national agencies as well. And currently we're focusing on quantum with the US. So recently the sanction order came. Then with the UK, it is almost finished with on machine learning and wireless and edge computing. And then with Finland on again wireless, which is again recently started another one. So we are about 138, peer-reviewed journals and conferences, about 165, and 4 patents have been granted recently as well in last 2-3 months, and a few book chapters and about 15 theses have been submitted. Some of our colleagues, former students are our colleagues now, so they're working as faculty in various places and postdocing abroad. This is something we do work on, which um, is actually one of the last things that came out from this thesis on visible light communication was on NOMA. We looked at how we can increase again the support more number of users in NOMA in visible light communication. So that was actually our first work, and which is here. So you can refer to this the first publication mentioned here, pre-coded design for Chebyshev-based and LMS pre-coded design for nonlinear LED composition, NOMA visible light communication system. So it is in IEEE came out in 2017. Uh, so here in visible light communication system, so basically if you're not familiar, I'll just give a small overview that we have been moving away from incandescent to LED lighting. Now if LED light are switched on and off so fast enough that as a human we cannot perceive they are being switched on and off, then we can do communication as well. We do something similar in a crude form in infrared remote controls that we have for television, for our air conditioners and others. So here we can use a visible spectrum, which is very huge, is in terahertz. So we have huge bandwidth. Okay, the practical things will limit it because LED has limited bandwidth and our photo detectors and our processing capabilities. But in theory, we have terahertz of this empty space that can be used. So here we are exploring the same visible light communication system for, let's say, downlink and uplink communication with different devices. So within your home, you could use your lighting infrastructure in offices or in other places uh, to lighting as well as do the communication, and inherently it is secure because it is within the same environment. So in this work, actually the last work that we looked at from Rangi's thesis was on applying NOMA, where we can support more number of users. Now when we are doing simulations and analysis, we applied some practical constraints on it. And we found out that as in Power Domain, might have had a couple of other talks before, and we'll cover NOMA and Power Domain NOMA here as well. So here, in case of Power Domain NOMA, for an LED, there is a practical limit. We cannot go to infinite bandwidths. We cannot go for infinite amplitude levels as well. So here. Because of these practical limitations, we and also we need some difference between the two users in the terms of, let's say, in voltages. If I look at, so we can have very limited possibilities here. So what we found, and we have seen in other literature as well, that after a few number of users are increased, let's say about 2-3 users are increased, after that we don't get that advantage. We start to lose the throughput gains that we were getting. So as practical limitations are there, but in case of RF work, we are not applied those limits as such, where we can say in theory that yes, you can go to infinite, but in practice it will not be possible. So this is one of first work actually we did on NOMA, looking at this adaptive signal processing or machine learning type of algorithms, doing a pre-coded design where we could compensate for the nonlinearity that exists because of the LED. We see the similar behaviors in RF as well, because in case of RF, we'll come to that actually. I think it's in the next slides. We'll come to that. So this is the work that I'll go much in detail later on. This is the work that we have been doing along with our collaborators from UK. Here we are looking at this heterogeneous network, where starting from 5G onwards, we have macro base station and femto base station. So macro base station is a base station which is similar to one that we have at the moment, working on UHF bands, and then femto base stations would be working on millimeter wave bands. So they work together. And then we have another angle you might have heard about or come across, device-to-device communication systems, where we are looking at devices talking to each other. So if I have two handsets, they are talking to each other, or one handset then working as a relay. So maybe it is in a area like, if you look at this figure, so you have DT, which is close to the FPS. It is getting signal directly from FPS, but then DR is the device which is receiving is further away. So DT could act like a relay and can transmit, or it can actually look at offloading some of the load from the macro base station to femto base station to form a NOMA pair, or even, but our focus is on pair, because in RF world usually we see two user being paired as in a NOMA setting. Okay, this is the work that we are. So I can probably skip this, not go much in detail, but basically I was just telling you about that we have been looking at survivability of optical networks. So this is where we are exploring if there is an earthquake or some other things happen, or there's a cable is cut somehow, then how we can route the data and through in a elastic optical network, which is um, thing which is coming in the future. Currently, the deployments are based on WDM, very fixed deployment, fixed allocation. So we can think of, let's say, if you're familiar with OFDM, so EON will be something like if you have, let's say, 32 carriers, and you want to give your data rate may not be enough to use all 32. You can probably use only 16 or 20 of those, but the remaining ones are getting not being used or not required to be used. So similar concept in case of optical networks, where we can use certain part of this OFDM frame for communication. Others can be used for some other from some other user. It can be used as well. Now in QKD, this is something which we are currently looking at, is on transmitting this quantum key distribution, quantum keys from Alice to Bob, and seeing how it can be. So we have a, if you're more interested in detail, you can look at our open access article in Journal of Open, so IEEE Journal on Communication. It is an open journal that you can look at. It's a full review article actually, so it will give you a basics of what is quantum and what people are doing at the moment and what we are also doing. So it's a review article that you can have a read. It recently came out in this year only. Then we're looking at performance list of multi-hop relay network. So here also NOMA can be used, but this was one of our early works where we looked at if we want to increase the coverage from, let's say, one room to another, then use multi-hop or cooperative network. So they have been known for many years, but we looked at some different architectures where, let's say, we have optical fiber connected to one of the nodes. They can, within the room, let's say you can connect through Wi-Fi or millimeter wave communication system. You can use beyond 6 gigahertz bands as well. And but between the two rooms, because of the attenuation from the wall, we can use a UHF link, and that can have another device which can convert it to millimeter waves, just to have a wider coverage. Basically, the goal is to have a wider coverage and pass through these walls or other features where the signals cannot. And this is the same problem we are going to see in the 5G networks as well, when the millimeter wave radios are switched on. And this is a very practical problem that we have known for many years, but most publications would ignore actually this limitation. So our focus has been looking at this practical limitation, where we looked at nonlinear distortions that are introduced by the nonlinear power amplifiers, which are there in a RF system in the front end of the system before the signals are put onto the air. So they are not linear device. If you look at this figure on the right hand side, output power, input versus input power, so the curve is not linear. In actual response, there's a slight curve. And if we are operating in this nonlinear region, then of course we need to use some kind of compensation, or our rates that we are expecting or we claim in an ideal system, we cannot achieve those. So we have done some work. This is a magazine article. You can have a look at this and some other research articles as well, where we have looked at higher order modulation schemes. So looking at 16 com, 64 com, 256 com, and then hexagonal com, which we are hoping that hexagonal com will become part of one of these beyond 5G standards, because it's a very interesting packing of the bits. It takes less energy than for the similar amount if a square com was or rectangular comms were used, and the performance is actually quite good as well. So it performs very well. So and with lower energy, and so it's one of the densest packing that you can get. So if you're interested, have a look at Starcom, hexagonal com. So hexagonal com, we have done quite a bit of work in different scenarios, looking at its performance. Recently, looking at how in energy harvesting also it can be used. So now I'll move on to the NOMA slides. So I'm closing these slides. I'm going to open slide on Power Domain NOMA. Okay, window. Okay, I'm making it full screen. Now, can you see the next set of slides?
Yes, sir.
Okay, thank you. Okay, yes. Yeah, so here we'll cover the motivation and some of the works that we have been looking at. So basically, so in wireless communication systems, they have evolved, you know, ever more, and we are using wireless more than the wired we used to have. So it is used for things like socializing, gaming, e-commerce, and we've seen now in the COVID era, there's a lot of work has happened because of the wireless communication networks. We are able to wireless mobile communication. We are able to, do these courses and do other uh, things as well. And our business has continued because we had a very good network in the cities and urban areas. Um, Now, data, as you know, has been increasing a lot over the last few years, and a lot of us are now consuming more videos and heavy data than the initial the communication system were designed for voice only, but now we are doing more of a data transmission. So the methods are also have evolved over the years to look at how we can use the spectrum more efficiently, use the timing slotting more efficiently. Um, Now, in the 4G communication system, they have reached a theoretical limit, and that's why we are moving towards the 5G era. So it's not able to sustain. So there's two things. One is the number of uh, users have increased tremendously, and with the users, I mean um, including the IoT devices. So now we are in the era where we, have IoT devices, everywhere. We have, we are using smartwatches, we are using smartphones, yes, and many of us are using, some of us are using like two phones at least, and then there's a laptop as well, and there's watch. Then we may have sensors, in microwave ovens, in fridges, which can tell us, if we're running short of something, looking at um our RO systems or our TV. So they're all in, and also in advertisement these days on television. You see, they are selling the IoT um, term. So there's a lot of devices, and what has happened since 4G has been there, we are seeing a lot of these devices now talking to each other. Now, as you move towards 5G, we are looking at things like you know uh, machine-to-machine communication systems. So machines talking to each other. And a lot of this communication, initially they were, initiated by a human being. So let's say I have to talk to you, I'll pick up the phone and call you, right? But now the machines are now talking to each other in logistics, in shipping, and a lot of other applications. So currently, as of today, we are about 7 to 8 times more number of devices as a human population on this planet. So that all this all needs to be supported through the wireless links. Now, till now, till in 4G, we have been going orthogonal, and even actually the first generation of 5G is also looking at orthogonal. So that's where we'll see there's a change, and there's an interest to go towards NOMA. So available bandwidths in 4G are again getting finished. It's again reaching the max capacity for the number of users. And achieving an idealistic 5G network would require a pioneering, research and new methods, and that's where NOMA and similar techniques have evolved. Now, these are some of the techniques which are looking at this challenge from the 5G point of view. We're looking at NOMA. So that's the main thing of this this program. Here we have millimeter wave. That's another contender. Then massive MIMO. So MIMO we heard about the 3G, 4G era. Now we're looking at massive MIMO for 5G. Visible light communication system we covered a little bit. That's another alternative for mostly for indoor communication at the moment. Indoor, but it is coming. It is that even the commercial deployments are happening for visible light communication system. So it's not only a theoretical, or a blue sky concept. Then of course cognitive communication, cooperative communication. So they have been there for a while. But again, they also didn't make it into the standards yet. But as we are now looking at various applications, we are looking at issues with the spectrum utilization. So this is where cognitive radio will come in, and cooperative networks in a new avatar of intelligent reflecting surfaces is making news at the moment. But cooperative network will come to the deployments we're expecting in the 5G era. So for multiple access, so multiple access, what does it mean? So multiple access is a scheme or technique which is used for serving multiple users. So here, when I say users, could be devices, could be IoT devices. It doesn't have to be a human being or communicating. So here we are looking at a multiple users over the same channel under a given protocol. So we as computer science engineers, we have ECE engineers, we have been teaching our students, and when we were also studying, we were told that we have to go orthogonal. So if you want to handle more number of users, more number of access given to a certain resource, you go orthogonal. Now that could be in different domains. It could be in a time domain, it could be in frequency domain, it could be in space domain, it could be in code domain. So it could be various domains, but the idea was to go orthogonal. Right, so if you just do a small recap. So in case of first generation communication systems, we used frequency division multiple access. Different users would be given different bands. They were separated apart by certain distance. So, for example, let's say I had a bandwidth of let's say 100 kilohertz, and I had 5 users. So I'll give them, let's say, around 15. So theoretically, I should give them 20 kilohertz each. So 20 kilohertz times 5 users will give me 100 kilohertz. But in practice, because it was again first generation, our filters designing and all, we need some guard band. So we will, let's say, give 15 or 18 kilohertz, leave this 2 kilohertz band, and try to fit the 5 users in. So here we are actually losing this 2 kilohertz guard band or 5 kilohertz guard band that we have given, but we had to give it because of the practical limitations, and to avoid this uh, inter-symbol interference or inter-carrier interferences. So here then we move to second generation communication system, which is 2G, which is very popular. So it is actually a combination of both frequency hopping and time division multiplexing. But here what we did was we looked at different time slots, and that's what our telecommunication systems are also, our landline phones and landline communications are also defined on the TDMA system. So it's a time division multiple access system where different time slots are given to different users. So this we can think of as a conveyor belt, let's say. So whenever there's your chance comes, you put your data onto that belt, and that belt actually moves very fast. So if I, let's say, have 5 users, and each one of has let's say sending one symbol per second. So this will be, this type of switch or a conveyor belt kind of thing will move 5 times faster, so that it can cater to each one of us and not lose any packet. So this required a good amount of synchronization between the transmitter and the receiver. So for example, if we lose the synchronization, so somebody else's packets may come to some other destination which were not initially defined for. So in TDMA, it is good. It is actually the most popular form of communication in the access network, on also in our this PST and what we call them as landline phones, where we connect to the telephone exchange, and then between the exchange there is another centrally exchange, then there's a trunk line. So they're all based on TDMA concept. Now in GSM we saw a combination of both, although it says TDMA, but it is TDMA with frequency hopping. So different users, the for same user, we don't give the same frequency allocation in that time slot. So as soon as the time slot changes, and these time slots are very small. We're talking in a microsecond time slots. So here, when the slot changes, then the frequency allocation is also changed. So it's called as frequency hopping. This then in third generation in 3G systems, we saw emergence of a code division multiple access. So where we again were trying to solve this problem of giving higher bandwidth and time slots to by giving orthogonal codes to different users. So in first generation we were giving a subset of the available bandwidth in the but we're giving the full time slot. In the second generation we were giving a full bandwidth, but we were giving the a slot, a time slot. So times was slotted. Um, and then in third generation, we said, okay, we can give you the full time and frequency, but we'll give orthogonality based on the codes. Then in the fourth generation, and that's what is carrying forward in 5G as well, we're looking at OFDM, orthogonal frequency division multiple access. Now, this technique has become very popular, and I think a lot of it goes to the credit to IEEE in case of the wireless LAN networks. So, wireless LAN networks are mostly based on they're actually based on IEEE 802 series, which is based on OFDM. So, OFDM became a choice of a standard, and that provides so it is similar to FDM, you can say, but here, so it's a frequency division multiplex, but here the carriers are orthogonal to each other. So that helped us in saving on the losses that we had when we were putting a guard band, because guard band we were not transmitting anything, so it was a waste. So we tried to utilize that waste by assigning orthogonal carriers and transmitting our data onto them. And again, the implementation was very easy. If you have worked on that, basically you have to use serial to parallel converters. We'll have to use a FFT, IFT blocks, and the the silicon technology also we can get off the shelf chips for doing this, so they very efficiently. So the whole ecosystem was formed around this. So OFDM, and the performance is very good as well for 4G as well. You are seeing it even in case of mobility and other cases, it is quite good, and hence it became popular in satellite communication system or direct to home the entertainment systems as well. It is also DTH systems too. So OFDM was the different frequency bands are used, which are carriers are used, which are orthogonal to each other, and that's what we have told, and that's what we teach as well in our. Yes, if you have to serve multiple users, and if you go orthogonal, then there is no interference users, and it's a perfect system. Um, but NOMA breaks that thing. So it, in a way, I'll say a revolutionary thing that uh, we are told to think we can also go non-orthogonal um, and still serve more number of users. So NOMA has activity. So these are the two main broadly domain and core domain. Other variants will pattern domain and others. So, but mostly there are two main categories: a power domain NOMA and core domain NOMA. Core domain NOMA is also known by SCMA name as well. So there are two main common. But SCMA is more popular name now, but essentially it is a core domain NOMA, where we are breaking the non-orthogonality in the core domain. Then PD NOMA is something that we have actually mostly worked on. We did some work on SCMA as well, but very limited. And our power domain NOMA exploits the this power diversity between the two users. Now, core domain NOMA exploits the core domain or non-orthogonality resource allocation. Now, power domain NOMA is simple to implement. I mean, you can, if you've done, let's say, an OFDM implementation or a simple, don't even use even OFDM. If you use a simple uh, uh, a communication system implementation or MATLAB, so you can do PD NOMA very easily in just a few days effort. Very basic implementation, so not talking about the full stack, but it is easy to implement, and it is compatible with the current requirements of transfer. So I can use the current 4G baseband and RF chain by changing the firmware, changing some things in the on the pre-processing side, and rest of things can remain the same. So I don't need to change the RF chain for this or change the bandwidth requirements or others. But whereas for SCMA, we need to do, because it is similar to CDMA, which requires the huge bandwidth, and so those requirements are not there for Power Domain NOMA. So that's easier and more easy to integrate within the existing infrastructure of 4G or Wi-Fi type of networks. Now here in this work, we'll focus mostly on application analysis of Power Domain NOMA, hence, and Power Domain NOMA basically exploits a new dimension. So far we have seen that you can do orthogonality in time, you can do orthogonality in frequency, you can do orthogonality in code. Now here we are exploiting in power domain. So we are going to give we are saying that there is another dimension which is in power. So here we can give different power levels to different users uh, for multiple users, and use um, some kind of algorithm called as SIC, successive difference cancellation algorithm, which can um, have this non-orthogonality user. Now, the development of superposition coding and SIC technologies, both in theory and practice, guarantees and at the receiver we use SIC. So SIC, if some of you read about let's say MIMO detection or MIMO receivers, even about yeah, closer to 2 decades back, so it was late 1990s. With hello, so can you see the next slide, which is figure 1?
Yes, sir.
Okay, thank you. So here, this figure is very important. So I just want to double check, because with this figure we can understand some of the basic concepts of power domain NOMA. So here we have a base station, which is when we're looking at a downlink scenario. So the base station is transmitting to two users. So UE1, user equipment 1, user equipment 2. So these are two different users. And one user I can, I'm using color coding. So I'm using one user as, so UE1 is blue color and UE2 is green in color. So here, at the so my goal is that okay, they are both the users are in the same direction, so I cannot give them a spatial diversity. They're in the same space, same direction, and I want to serve them in the same time and same frequency slots. So let's say my subscriber Airtel or Vodafone or Jio gave me the 6 megahertz of band, and or 2 megahertz of band. Within that band, I need to look at the I need to transmit the signal. Now I have these two users, UE1 and UE2. They both need to be served at the same time and same frequency. Now I can do it by giving them two different power levels. So if you look at this plot here, the power and frequency, we have the blue color is given us lower power, and the farther user is given a higher power. That's a green color one. So here we just sorry, just a minute.
Sir, you are not audible. Bhatia sir? Sir, you are not audible.
इनको चाहे ऊपर ही बुला लो हाँ. Hello, yeah, sorry, there's somebody on the door. Basically, yeah, so here we are looking at this power diversity. So I'm going to give higher power to the user who is further away. Um, and then user which is closer, I'll give them lower power, which is this blue in color. Um, um, and then I will superimpose them, so I'll add them up and then send it over the same channel. So here at the receiver, I'll have a SIC, successive interface cancellation in case of, so the idea is that the UE1 will be able to cancel the interference from the UE2's signal, and UE1 signal can be decoded then once the UE2's interference has been cancelled. Um, then in case of UE2, because it is further away, we may not need to use a successive interference cancellation. We can directly decode UE2's signal. So here, the idea is that we are. So I mean, you can say that I could have done this before as well in previous systems, but here I'm adding some interference. Right here, the interference is added, uh, but in a controlled fashion. So that is the key here. That because of this adding of this interference, I'm able to serve more number of users. So here in this example, because at the receiver I'm using SIC, I can cancel the UE2's signal, which is a higher power. The principle is to first reduce the interference from the highest user. So that's what we can highest power user that we are doing here. In case of UE2, because it is further away, it is far away, and because of the path loss, the UE1 signal will be lower because again the gain that we're giving it is lower at the transmitter as well. So both there will be loss for UE1 and UE2 both, the green and the blue one. But because UE1 is already a very small value, we're given a very small gain to it. As it goes further, reaches UE2, it will be very small and can be considered as noise. So it is still there, but it's very small in amplitude or in a power level, so you can consider it to be noise. Hence, we don't need to use SIC at the user equipment at the UE2 to cancel the signal of UE1. So this is the basic principle behind a concept behind this power domain NOMA. I hope that is clear. So now advantages of NOMA over OMA. हाँ आपको ना वो ब्लू पेन से कर दो साइन इसमें जहां जहां ब्लैक से करें ब्लू से कर दो वो नीचे ही वेट कर रहा है
Sir, you are not audible.
hello yeah can you hear me now I don't know what happened can you hear me now
Yes, sir.
Yes, sir, you are audible now.
hello hello can you hear me now
Yes, sir. You are now audible.
okay thank you
Yes, sir, you are audible.
yeah I don't know what happened yeah okay so here yeah so we had this OFDM where we have we're giving so in OFDM we're giving orthogonal slots so we're giving bandwidth half of the bandwidth to UE1 and UE2 in what happens currently and the rate for the first user UE1 is 3.33 bits per second per hertz and R2 is 0.5. Now in case of NOMA, if I'm giving them the full bandwidth, so they're getting the full bandwidth BW complete, but I'm giving them a different power levels. So power level is 1 by 5 for the UE1 and power level 1 by 4 by 5 for the UE2 because UE2 is further away. So whichever user is far away, I'll give them the higher power at the transmitter. So with doing that, the rates for both have actually increased. The rate for the first user has increased to 4.39, and rate for the second one came out to be 0.74. So they're up of 32 and 48%, and I'm still serving two users. Now, in our work, we have actually seen that you can get gains of over 100% in certain scenarios for different users, either for the for the user which is nearby or the user which is far away. Our main focus of the work has been basically on the far away user. And there's one more thing I didn't go much in detail was that NOMA as such is a more fairer scheme because what happens currently that this allocation is a very the allocation of spectrum, these slots, this is very rigid and fixed. So we actually cannot change this allocation. Although my requirement, let us say, may not be to use the complete slot. So if let's say I'm using a small device which has to just send a few kilobytes of information, I'm currently given the same slot as given to someone, let's say, who is watching a video. So what will happen? Let us say another user who has much higher requirement will not be allowed in because there's no resource available. Both the users are given these slots. But in case if you're using NOMA, what we could have done is put these two users together because one has a higher rate, other one has a lower rate requirement, and freed up one another slot for somebody else. So it is a more fairer system to implement. Now let's look at what we have been focusing on. We'll look at a wireless channel, which has a fading of small scale and large scale fading. So small scale fading, generally we will model them as relay distributed, and large scale fading is large scale path loss is given by this formula, which is based on the distance. Because here, in case of power domain NOMA, the distance is key. So we have to. So the first thing that we have looked at is cooperative scheme for user fairness and performance analysis in NOMA. Since our most of the work has been on the mathematical analysis, so here we have used a very popular kind of distribution on how these nodes are distributed in a space, which is called as a Poisson point process. So here, what we say basically, the users are randomly placed, but how their distribution is, that is governed by this Poisson point process. Now, in traditional cellular network, it is unable to withstand the surge as we have before in our talk have covered. Now, the increased pressure on handling these number of users comes to the macro base station. But with coming of 5G, we are looking at femto base stations or small base stations, which will be having higher bandwidth, lower power, and small coverage area. So we are looking at a hybrid type of environment. Now, if you want to increase an MBS is difficult. It is expensive. Also, a lot of planning is required. Whereas FBS or small base stations can be deployed very easily. Um, and you can think of it even less like we are seeing nowadays. We have the Wi-Fi, so you can connect to your cellular network through the Wi-Fi. And as soon as you go out of your home or office environment, you can connect it to the cellular network. So something like that is a heterogeneous network. But here our focus has been looking at how they can do the load sharing. If that's a number of users increases, how we can use a NOMA pair or DUD pair to try to reduce some load on the heterogeneous environment. Heterogeneous this network. Now, device-to-device communication, as I said, is also receiving great attention, and D2D communication, the base station is bypassed, and communication takes between the two devices itself. Right? So D2D can occur in two modes: in band, which is in the licensed band, or out of band. Now, this is something which is debatable, which is still not decided. And see, if let's say you have a device which is talking to another device, so which is, let's say, close to you. So currently, let's say two of your friends are standing next to each other, but they are on same or even different networks. Even in same networks, the call initially goes to the base station and then is routed back to your friend, which is who is sitting just next to you. But what can happen is that these devices can talk to each other on the network side. Run their businesses. So this commercial aspects are also there, but theoretically it is possible. We can have two devices communicating to each other, so we are doing it already using Bluetooth or other devices. So why not for cellular network as well? Um, But yeah, that's another solution. So here what we have looked at, okay, that the D2D, we're assuming the D2D communication exists, and one of the D2D communication systems can be used as a cooperative relay. So if you are, let's say, two users, one user is closer to the base station, that can act as a relay and transmit the information to the device which is further away from the base station. So now let's see how we do this. So we have a tier selection or offloading in HETNET. So in this work, we do offloading as a maximum long-term average BRP or bias received power at the user. A user offloads to the tier with higher BRP. Thus, the offloading probability is given by this equation here. Basically, we have a bias for a MBS and a bias for FBS. Then we have these different path losses. And then we have a typical user from macro base station and the base station respectively. Now, when a bias factor equals 1, it is termed as a unbiased association and is similar to the conventional one where the user connects to the base station that offers the strongest power. So this is if let's say BM and BF they were both equal to 1. In that case, it will be similar to the conventional or the one that's existing where the user will connect to the strongest power that is it is receiving from. Now with BF greater than 1, the coverage of FBS is extended. This allows for tier selection to be tuned for load balancing. This is what we are considering here. Now in the proposed system model, we have got a HETNET comprising of a macro base station underlaid with a femto base station and spatial distribution of nodes followed by independent PPP distribution. So because we need to distribute them different nodes. Now there are different ways to do it. We can do it as a PPP, which is the most popular one and something that we use in the beginning. So PPP is denoted by this omega M and omega F for macro base station and femto base station respectively. So they are both distributed randomly. Now FBS transmits at a power level PF using NOMA and MBS transmit at power level PM. So we are using the subscript F for femto and M for macro. And YM and YF denotes the coverage range for MBS and MBS respectively, and macro user connects to the MBS according to the nearest neighborhood connection policy. That's a very simple policy that is used. Now, bounded path loss model is considered here, and the offloaded user is paired with a femto user available at the FBS and termed as a pairing user. Because one thing we need to know for NOMA to work, because you're doing non-orthogonal multiple access, so you need at least two users. And our focus and most of the research work mostly focuses on this two user case, and then we can generalize it through more numbers. So our focus will be on the two user case. So to distinguish the users with different channel conditions, the users are termed as a cell center user and a cell edge user. Now, as I was telling you previously, that a user which is closer to the base station will get a good channel. So either we can call it as a near user, or other definition is a cell center user, which is closer or closer to the base station, gets a stronger signal from the base station. Then the user which is far away or further user also can be termed as cell edge user, has a poor channel condition or weak or is a far user. So we are considering two of these users, CCU and CEU. You'll see the same term in the figures as well. And we consider two different cases. In the first case, the user offloaded from the MBS tier is served either as a edge user or as a cell center user, because what can happen, let's say in the MBS, the macro base station, you don't have any further capacity to serve a user. What you will do, you will try to offload the user to femto base station, and that is the full purpose of having a SBS, a small base station, that they will have higher user handling capacity and higher bandwidth as well. And the macro base station will then offload this user to the femto base station. Now for femto base station, this user can either be a cell edge user, or it could be a cell center user because it is closer to the femto transmitter. And in case 2, when user is offloaded, a corresponding primary user is searched with respect to the condition of the offloaded user. So In the case one, we are saying that as the user is offloaded to the femto base station, it will be either a cell center or cell edge user. Whereas in case two, I'm not sure. We say that the offloaded user will be actually a secondary user. So I'll make it as an edge user. In that case, I'll have to use for a pairing user. So I'll have, because in NOMA condition, we need to have a pairing user as well. So and based on this OU, we need to have a corresponding PU. Pairing user has to be there. And then there is another, so this is the figure that is, our system is. So we have a macro base station, we have different femto base stations. So they are connected through this. So D is for the device. And this dotted one is we are using for offloaded CCU. And the solid one is used for offloaded as CEU. So if you look at this figure, we have this solid one in the case one on the left hand side. In the B figure, we see this stroke. So here the user is offloaded as a cell edge user. So here, yeah, we have this dotted one. So we have cell edge user, or we can consider this to be a cell center user as well. So there's two cases that can in the case one. In case two, we are using a device D2D communication system to form a pairing user. So we'll have a cell edge user which is offloaded, and then we have another user which is going to be helpful in the pairing of these two users, because in NOMA we need at least two users to be there. Now this is another important criteria when we are saying, because we're going to pair the two users. Now how do we pair the two users? Now this is termed as NOMA compatibility. So NC probability determines whether the OU is offloaded as a CCU or CU. So either a cell center user or a cell edge user with respect to the primary user. Because there's a ratio that needs to be satisfied, and that will define if it is a cell edge user or cell center user. So the corresponding PU, pairing probability, refers to the probability of finding a corresponding primary user for a offloaded user. Now here we can calculate the total outage probability. So for the case one, so MU is offloaded to FBS. So the macro user which is offloaded to the femto base station or small base station basically. And this is done without NOMA. If let's say the slots are available, we can do without NOMA as well. And if with NOMA, then I need a compatible other user as well. Now the probability of this offloading changes. Now if MU is offloaded as a CEU at FBS, then this is the other equation that we get. So there are two cases. As a orthogonal pair, that's the equation number 2. Either it is offloaded as a NOMA, but it is offloaded as cell center user. And the third case is it is offloaded with NOMA, but it's is going as a cell edge user. So we did some simulation here for a typical user and offloaded user, what kind of outage probabilities we get for different SNR levels. Yeah, I'll probably go to the other slide here, which shows the difference between the two. So if let's say in the case one, so when this you see P as 0.5, this actually means it is offloaded, but offloaded as a orthogonal user. So here, because in the power domain in NOMA, we need to have this difference in the power levels. So the second case we look at, so within the case one, we look at the second option, where a large value of P denotes a difference between the channel gain between OU, offloaded user and the primary user is reduced. Is reduced to as compared to 0.1 and 0.5. Now, when MU is offloaded as a CEU, a lower or a better outage probability. So outage probability has to be as low as possible. So here a lower outage probability is achieved as compared to when MU is offloaded. Now difference in channel gain for rho is equal to 0.8 is less. However, the power allocation coefficient remains the same. So here what we are seeing is when we are doing offloading as a NOMA pair, we are actually getting a lower outage probability. Then we can also use a device-to-device communication. We mentioned in this slide here. So in this figure, we had this case 2 where we are using device-to-device communication system. So this will, so then there will be no more number of conditions that needs to be added. So in case 2, a corresponding user is searched for OU similar to the previous one. But if an incoming offloaded user is a CEU, a corresponding CCU is used. While if the offloaded user is a cell center user, because it is randomly distributed, it may happen that the user is actually very close to the femto base station, hence it becomes a CCU. So CCU, a corresponding CU is searched. Now, a situation may arise when OU is CU and FBS cannot find a corresponding pair. Now, in that case, NOMA and D2D tier can be used, which enable us to deal with this situation. Now, in a D2D group, the D2D transmitter serves more than a single D2D receiver using a NOMA pair. Now, this work designs. So in this work, we have actually designed this analytical frameworks for D2D pairing and all. We'll just look at that in short. So we can do this femto base station is there. So we have a cell edge user, which is available for pairing, and then we have a cooperating device, which is going to help us find a CEU. In other case, we have a femto base station where it's connected directly to CE, the cell edge user. The other one could be a cooperating D2T. So here through cooperative network, we're getting the signal across. Here we have seen that if we use this kind of a scenario, this kind of setup, then we can actually gain a lot. We are seeing a gain of an increase of about 42%, 55%, and 86% for different values of SNR. So there's a overall an improvement or decrease in outage probability by using the considered scenario. And if you use a D2D in case the previous ones were not possible, then also we have a decrease of 21%. So with D2D communication as well, we are improving the throughput and reducing so we're improving the ergodic rate, we're reducing the outage probability, and some ergodic performance is also improved. Now this is another interesting aspect. So I'll actually, yeah, so just to quickly go over this one. So we have this, as I was telling you, then we are looking at this hybrid networks. So we have a sub 6 gigahertz system, which is, let's say, your macro base station, or you can get this 900 megahertz range. Then we have a millimeter wave femto base station. Now they could be co-located as well. Let us say we have this or close to each other. In a communication system, the receivers, they do a channel estimation, and then they will send this information to the transmitter, which can be again used for pre-coding. It can be used for beamforming and other checking the quality of the signal, and then it can also change the modulation technique. So it is a set practice in the standard as well, that we do the channel estimation and then send this information to the base station, but onto a signaling channel. But again, we are not sending the exact values. There's a quantized values are sent. So what we have looked at here is, let us say I have this partial CSI. I don't have the complete channel state information, but even using this partial information, how my system will perform. Can I do better handover? Can I do better beamforming if I can assist this, or they are very close to each other?
Capital M. Mathur Anna.
So NOMA enhances spectral efficiency, increase. So this is what we have seen already. Cover transmission in millimeter wave, because the NOMA is compatible with, or it can be implemented as with millimeter wave, with massive MIMO, with full duplexing, with visible light communications. So it is change how multiple users are served. So here we have tried used it with millimeter wave, which suffers again from high attenuation and high sensitivity to blockages. Now the directional nature of millimeter wave requires, or it improves, if we use some kind of a beam training. So we use beam forming, but doing it alone on millimeter wave requires high complexity and takes time as well. So reduce that, we can do in a two-stage. We can do this thing based on first on sub 6 gigahertz, which gives us a crude, let's say, estimate where the user is. And the information can be used by the millimeter wave base station to further, let's say, fine-tune it. So what we are saying that in the future we are looking at multiple RAT, multiple radio access technology, where they both will be communicating, or will be co-located or very close to each other. Now here also again NOMA can be used. We have seen, if we use the cooperation between the two base stations are happening. Then this is a typical setup. I'll then probably skip directly to this. I'll skip this one. So if you can refer to the papers in detail. But I just wanted to show you what advantages we can get by using this multi-rat system. So here, in case of a ideal case, what we have done is we have considered a case to check the viability of the system as well. That let's assume, because simulated environment, we assume that we exactly know the CSI at the base station, which is the ideal case. So here we'll plot the ideal case one where the CSI is already known, the pink or magenta line. But in the other case where we don't know, we are estimating it and we are setting in the partial information to do beamforming or helping it. So here the rates have, the outage probability has is not as good, but this is a more practical scenario. And similar thing I will look at here as well for the case B as well, that yes, there is. But if we are going to do this multi-rat system where both are able to share the information. So this is one assumption here, that millimeter wave and the femto-based and the macro-based station are able to share information. There we can see a gain of 60% to 45% as such. The similar thing for different scenarios we have tried. So summary, basically a coexistence of multi-rat technology in future networks we'll see in NOMA heterogeneous networks. We can see that the partial CSI case also it works better because that is more practical. That is what happens. And if they both are talking to each other, there's a two-step association, but this can actually help in beam training and so it is much faster training and more practical solution, and blockages are an integral part of communication, so they can be helped out. We can also use so yeah, I think in conclusion I can say that we can also use intelligent reflective some of the new things that are coming up. So then can also use is nice, compatible with future technologies like IRS when we're talking about HAPS, high amplitude communication systems. So HAPS and others. So there it is compatible not only with the existing technologies but in future proof technologies as well. For details, yeah, you can look at these publications in detail, and we can discuss some now as well. And some of the key references there is another very good article by Zinghording, which covers the different myth and any confusion that you have about NOMA. So they have this article which covers a lot of these issues where a lot of people make assumptions and they may not be applicable for NOMA or not. So they've taken certain cases. Not sure if it is mentioned here, but if you just do a Google search with his name and look for, and I think it's Waziri as well from the US and Poor. So they have given this paper which is on common myths of NOMA. So you can clear some of your doubts that you have reading. It's very easy and interesting piece of work. And now, going forward, we are looking at this designs. If you look at this last one, that's looking at a simple design for IRS NOMA. So we are looking at these designs currently in our work. Okay. I think open for. If it's okay, we can open for questions and answers. Hello, Garima madam, is it?
Yes, sir. Yes, participants, if you have any query, you can unmute yourself.
Sir, good morning. Good morning, sir.
Good morning, sir.
Yeah, good morning. Good morning.
This is Dr. Yes. Sir, my question is, what is the main observation that we need to make when we have information about CSI and partial CSI?
Sorry, what was the question? So the question on CSI and partial CSI, but I missed the middle part.
No. What is the main change in performance of the system? We have complete information about the channel state, and we have partial information about the channel.
Okay, sure. Okay, I'll move on to this slide then. Okay, coming for me. We'll attach it again.
Hello, good morning, sir.
Yeah, good morning.
Sir, if possible, share the PPTs and request to madam, please share the recording at the end of the day so that we can revise our topics.
Definitely, sir. We provide all the material and PPT to all participants after the session completed.
Okay.
Yeah, so let me answer this. Yeah. So if you look at this slide here, so we have these results. So the first one, this magenta line A, right, which is sub 6 gigahertz, you get perfect CSI. So perfect CSI, we get this nice waterfall kind of outage probability. But here, in case if the partial CSI is known, then we see a reduction in the outage probability. So we've tried it for both in group 0 and group 1. The same thing we are seeing here is that you will see a reduction in the outage probability because we are using a partial CSI. So the amount of reduction, yeah, you can, from this figure we can see, it is, let's say if I look at figure number, so we are, let's say, losing about 6 to 7 dBs, and then the gap starts to increase, increase the SNR levels. So around, let's say, 40 dB, actually a loss of about 10 dB. But if we are not using the partial CSA, then the performance is even poorer. So if you look at this, if no feedback scenario, we have an improvement of close to 50%. Similar thing we see for simulation conditions. Right, and if let's say you're interested to in detail, refer to our paper. So there's more detail on that and more simulation results as well.
Bhatia sir, you are not audible.
Oh, hello. Yeah. Are you able? Yeah, madam. Yes. So, any other question from participants?
Yes, sir. Good morning, sir.
Good morning.
For communication, wireless communication purpose in the 5G network, at the transmitter and receiver, what type of antenna, whether the highest bandwidth or lowest bandwidth, we should prefer for that?
No, sorry, I didn't get the question. Something about the bandwidth, right?
Am I audible, sir?
Yes.
Sir, I need to know for communication purpose, sir, at the transmitter and receiver for 5G network, whether the bandwidth should high or low.
Okay. Actually, there's a lot of echo. So what I understand, you have some question on the bandwidth to be higher or lower.
Yes, sir. For antennas,
And
related to antenna.
antenna. Okay, so there is because of this, coming of 5G. So there's higher, yeah, interest in the research, in the antenna as well, because we are looking at higher bandwidth, and that too we are looking at higher carrier frequencies. So here we're looking at, let's say, 27 gigahertz, or now even higher, 70 gigahertz as well, and 30 some bands as well, around 30 gigahertz range. So for those, of course, yeah, need to have a different type of antenna designs, and the bandwidth as also, we are looking. So let's say currently for Wi-Fi, we are looking at 20 megahertz, or but here we are looking at 100 megahertz, or even higher. So we need to have antennas which can have this flatter responses, and that too at a higher frequency.
Okay, sir.
Yes, any other query? Any other query? Sir is waiting for you, participants. I think, sir, there is no one query. Thank you so much for this wonderful session, and I hope all the participants must have benefited for this session. I request you to all to kindly turn on your camera for a group photograph.
Sorry. Okay. Thank you very much, and thank you and congratulations to your team for organizing this. And usually very busy few days for your team.
Yes, dear all, turn on your camera for a group photograph. Bhatia sir, kindly stop your screen share.
Okay. Sorry. Yeah.
Yeah, thank you everyone. Next session will start at 11:30. So I requested all the participants join at 11:30. Thank you, sir.
Okay, thank you, madam. Please to be there, and all the best for the rest of the session. Thank you.
Thank you, sir.
Thank you, sir.